right, let's do Lewis dot diagrams for molecules or teams of elements together, which we mean a polyatomic ion. So either a molecule or a polyatomic ion, which this video is calling a team. All right, so just some background information about Lewis. Lewis was a chemist that started at Harvard, finally ended up at UC Berkeley. He went from Harvard to MIT, Massachusetts Institute of Technology, and finally ended his career at UC Berkeley. In 1910, he made UC Berkeley's chemistry department its entire own separate school. And on March 23rd of 1946, Lewis was found dead in his UC Berkeley laboratory, where he'd been working with hydrogen cyanide, and lots of people speculate that maybe he killed himself with cyanide, considering he obviously knew that it was deadly. So you should already know that atoms share electrons in order to create a stable noble gas configuration. So the valence electrons are in the outer energy level. You should already know that. And you should know how to figure out what is the number of valence electrons. There's a Roman number on each of the tall columns, and that Roman number tells you how many valence electrons that element has. And so we only are doing it for the tall columns. We do not do it for any of the D or F sections of the periodic table. So we're going to only be doing it for the 8 tall columns, and the valence electrons are the number found over top of each of the columns on the periodic table. So we're going to copy down the rules, and at first the rules might not make any sense, but just copy them down so that you have them for when we do our practice problems, and that way you also have them on test day. So rule number 1 is draw the skeletal structure of the molecule and connect the atoms with single bonds. So a dashed line shows an electron pair. So a dash is equal to 2 electrons. So the first step is draw the skeletal structure of the molecule and connect the atoms with single bonds. A dash is a single bond. So 1 dash equals 2 electrons. Rule number 2. Count the total number of valence electrons present for each of the elements that you have. Be careful of the charges. Remember that if you have a negative charge, it's because you've gained electrons. So you'll add electrons. And if you have a positive charge, it's because you lost electrons. So you'll subtract electrons. So you're going to count up the total number of valence electrons for the elements that you have in your formula. The third rule, complete the octets on the outside atoms. So an octet means 8. So every element needs to have 8 electrons, except there are some exception columns, but the majority of the elements, the octet rule is what we apply. So we distribute our electrons, giving everybody 8 electrons. If you have too few electrons, like everybody doesn't have 8, unless they're an exception to the rule, which we'll go over those after we go over the rules. But if you have too few electrons, then you're going to create a double bond or possibly even a triple bond in order for everybody to get their 8 electrons. Double and triple bonds are where electrons are sharing. If you have too many electrons, then you're going to go ahead and place those on the central atom. So you'll draw like an imaginary box around the central atom, and you'll put a pair of electrons together on the central atom. Now, all of our electrons will always be in pairs. In Chem 1, we don't do any of the exceptions where they're single atoms, single electrons. So you'll always have an even number of electrons when you count up. If you have an odd number of electrons, it means that you've probably had a charge on it that you forgot to count. So there are some hints. Hydrogen is terminal. The word terminal means it's on the end. So if you're debating and you have more than two elements and you're wondering where to put the elements at, hydrogen is not going to be the central atom. It will be on an outside end. The loner element is always in the middle. So when you have a formula, typically you have one element that's by itself, especially in Chem 1. When you get to Chem 2, there's some differences, but our elements, for the most part, will just have one loner element. And so that guy is going to be your central atom. He'll go in the center. So the loner element is going to be in the middle of your diagram. Halogens are also usually terminal, so they're on the outsides. So if you're deciding, if you have the same number of elements and you're deciding where to put an element, hydrogen's terminal and halogens are terminal. So hydrogens and halogens are terminal. Unless they're the loner, then they're in the center. So there are some exceptions to the octet rule. The columns 1, 2, and 3 are happy without having 8 electrons. So elements from column 3 are happy with 3 bonds, elements from column 2 are happy with 2 bonds, and elements from columns 1 is happy with 1 bond. So that means that elements in columns 1, 2, or 3 don't actually have to meet the octet rule. So if you're an alkali metal, if you're an alkaline earth metal, or you're in boron's family, which is basically boron and aluminum, as the central atom, then you don't get to get your full 8. So we won't borrow to make central atoms of columns 1, 2, or 3 happy. So we'll see when we get to 1, but elements in columns 1, 2, and 3 do not have to meet the octet rule. Elements in columns 4, 5, 6, and 7 all will need to have 8 valence electrons because they're going to gain electrons. All right, so let's start with CO2. The first thing is draw the skeletal structure. Who's going to be in the center? Remember, the loner goes in the middle. So I have 1 carbon and 2 oxygens. That means my loner is carbon. So carbon is in the middle and oxygens are going to be on either side. It doesn't really matter where in this illustration they put them just to the right and left, because if you're writing on lined paper, that's the most logical place to put things directly on the line. But it doesn't really matter where you put them. They're hybridized, which means they're spread apart as far as possible. So they're put at east and west in your typical hybridization. All right, so how many valence electrons does carbon and 2 oxygens have? You add them up. So carbon, look where it's at on the periodic table. What column is it in, and how many valence electrons does it have? So if you go look, you'll see that there are 4 valence electrons for carbon. Then go find oxygen. Oxygen has 6 valence electrons. And there are 2 oxygens in this formula. So I've got 4 valence electrons for my carbon, and each oxygen has 6 valence electrons. There are 2 of them. So that's 12 for the oxygen and 4 for the carbon, for a total of 16 valence electrons. All right, so I've got 16 valence electrons. We've already used up 4 electrons because each one of the sticks is worth 2 electrons. So just by making our skeleton, we've already used up 4 of our 16 valence electrons. So you're going to distribute the octets next. Remember, it says distribute the octets. So we're going to start on the oxygens. You always give it to the kids first. I kind of create myself a story where this is a family and mom is here in the middle and these 2 are the kids. So mom has 16 electrons to give out. She's got 16 goldfish, and she's going to give her kids the goldfish first before taking any for herself. So each of her kids needs to have 8 goldfish. So she's going to distribute those goldfish, we'll call them, to the electrons on the outside. So we're going to give each one of them the electron. So I've already used up 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I can't draw any more dots because I only have 16 electrons to distribute. Remember, carbon brought 4 valence electrons and each oxygen brought 6, so I only have 16 electrons. And this is me distributing all the electrons that I have. Is oxygen happy? Well, it's happy if it has 8 electrons. So remember, a stick equals 2. So 2, 3, 4. So a stick has 2. 2, 3, 4, 5, 6, 7, 8. Check, that oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. Check, that's oxygen's happy. Is carbon happy? And the answer to that is no, because carbon right now only has 4 electrons. Remember, each stick is worth 2 electrons, so carbon only has 4 electrons. So you got to go to the rules. What do the rules say if you had too few electrons? It said if you had too few electrons to borrow some of your electrons and share them with carbon. So you're going to have to share them. So everybody does not have 8 in this. The octet rule has not been met for carbon. So if not, you're going to remove a pair of electrons and turn them into a line, which is a shared pair. So remember, a stick equals 2 electrons. So you're going to take away, and it doesn't matter which electron pair you take away, but don't take one from here and one from there. Whichever side you take, make sure you take them from both together. And you're going to create a shared pair of electron. Now, does this oxygen still have 8 electrons? Yes, 1, 2, 3, 4, 5, 6, 7, 8. So I currently have 8 electrons. So this is 4, 5, 6, 7, 8. Okay, so I have 8 electrons here on this guy. The next thing I'm going to do is see, do I have 8 over here? Well, sure, I still do because I didn't do anything there. But carbon now only has 6 electrons. 1, 2, 3, 4, 5, 6. So now I need to share again. Now, don't make this guy share again. Okay, go over to this kid and make this kid share. So take away 2 electrons from that guy and make him share. Now, this oxygen has 8. This oxygen has 8, and this carbon also now has 8 electrons. So now everybody's happy. So this is a completed Lewis dot structure for this molecule of carbon dioxide. Okay, so everybody's happy in this. Carbon is not in an exception rule, so you have to make carbon happy. Carbon is in a 4 row, and so everybody 4 and up has to be made happy. All right, so let's try another one. This is a perchlorate ion. This is what this is. So it's an ion, so it's got a charge. So the first thing I need to do is draw the skeletal structure. So who's going to be in the center? I've got 1 Cl and I've got 4 Os. So who goes in the center? Draw the skeletal structure. Then I have to count how many valence electrons. So how many valence electrons does that have? So I've got 1 chlorine. That means I have 7 electrons, and I have 4 oxygens. And each oxygen is worth 6, and I have 6 times 4. So I have 24 valence electrons for the oxygen. And then you got to figure out, what does having a -1 charge means? 1 more electron. So you're going to add an electron because of that -1 charge. So it's 24 plus 7 plus 1. All right. So draw the skeletal structure and then distribute your electrons. You have 32 electron. That's not negative 32. That's valence electron. That's the symbol for valence electron. And so you have 32 of them. So how many have you already used just by making the skeletal structure? Remember, each stick is 2 electrons. All right. So I've already used up 8 electrons when I start counting. So I typically start by saying 8 and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I've distributed 32 electrons. I had 32 electrons to distribute. Then I've got to ask myself if each of the members is happy. Double check if your central atom is in an exception rule before you start borrowing. Chlorine is not in an exception rule. Chlorine brought 7 electrons to the party and is expected to get all of the electrons, so it's expecting to get an octet. So, is oxygen happy? Each one of these oxygens has 8 electrons. So if you count them up, you'll see each one of the oxygens has 8 electrons. So yes, it's happy. And is Cl happy? Yeah, Cl was happy the minute I made my skeletal structure. So chlorine is also happy with 8 electrons. So this is my completed Lewis dot structure for a perchlorate ion. All right. So draw the skeletal structure for this sulfur trioxide. So who's going to be in the center? Who's the loner? S. And then your rest of your skeletal structure is going to have 3 oxygens. So it doesn't really matter exactly where you put them. Typically speaking, I would have maybe hybridized these from the get-go. In our next PowerPoint on shapes of molecules, you'll see that for our class, I won't make you redraw them just in the interest of time. But when you get to college, after you distribute all the electrons, you have to look up what shape it's going to create geometrically and redraw them in the right fashion. So for me, it doesn't really matter where you put your oxygens right now, and I'll show you in tomorrow's lesson how do we know where it actually would go, whether or not it would be this shaped or another shape. All right, so we've got valence electrons to count. I have 1 S, and each S has 6 valence electrons. I have 3 O's, and each O has 6 valence electrons. So my total of electrons, 6 plus 18, is 24 electrons to distribute. How many electrons have you already used just by making the structure? The skeletal structure has already 6 electrons distributed. So when I start counting, I already start with the number 6. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Then you have to ask yourself, is your central atom in an exception to the rule? So remember, that's columns 1, 2, and 3 have exceptions to the rule where you will not borrow to make them happy. But sulfur is not in columns 1, 2, or 3. It's in column 16, which has 6 valence electrons to contribute, which means you do need to make it happy. So sulfur is not happy with just 6 electrons, so you will need to share electrons to make them happy. It doesn't matter which of these oxygens you make share. And by the way, we're going to make somebody share, but this kind of molecule with 3 oxygens on it the shared electrons are going to do what's called resonate, which means although I take them from this guy and share here, in a second from now, or even not even a second, in a picosecond from now, those two electrons will be back and this oxygen will share. And this double bond will resonate or switch locations around this molecule nonstop. So just because we borrowed and made it look like this oxygen gave it, this one won't be giving it the whole time. It resonates. This double bond switches locations and the shared electrons will switch nonstop. All right, so choose any two electrons. It doesn't matter. Make sure you choose two that are next to each other. You erase them and you create a shared line. So when you did it, you could have shared those electrons, or you could have erased these and shared them. You have to pick one pair, it didn't matter which pair you picked, and share them. All right, so let's do, this is a nitrate ion. So when this PowerPoint said for molecules and teams, this is what it was referring to as a team. It is a polyatomic ion, which is, we've already used it in our naming principles, so we already know what it is. So the first thing is we're going to draw the skeletal structure and count the valence electrons. It doesn't really matter which step you do first. So this person counted up the valence electrons. I've got 1 nitrogen, and I've got 3 oxygens, each at 6 apiece for 18. I've got a -1 charge, so that means 1 more electron for a total of 24 electrons. Then I am going to distribute my octets. I'm going to check, is oxygen happy? Is oxygen happy here? Yes, every oxygen has 8 electrons. Is nitrogen happy? Double check, is nitrogen in one of the exception rules? Remember columns 1, 2, and 3, you won't borrow to make them happy. But nitrogen is, if 5, has 5 electrons, see? So if nitrogen, if your central atom has 1, 2, or 3 valence electrons, you won't borrow to make it happy. But nitrogen has 5, so he's not happy. What does that mean you need to do? It means you have to share electrons. So we erased these 2 electrons and we made a double bond. Now nitrogen has all 8 electrons that it needs, and this oxygen has 8 electrons, 4, 5, 6, 7, 8. Okay, so it's got all 8 of the electrons that it needs to be happy. All right, so we've created our skeletal structure. When we put the skeleton, we've already used up 8 electrons. How many total electrons do we have? So S is 6 electrons, and 4 O's is 24 electrons. A -2 charge on this sulfate ion means 2 more electrons for a total of 32 electrons. I've already used 8 electrons just by distributing the skeletal structure. So I start out with 8, then I say 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32 electrons. I've distributed all 32 electrons. Then I have to ask, is sulfur in a column that is in one of the exceptions to the rules? That's columns 1, 2, or 3 have exceptions. No, sulfur is in column 6. It brought 6 valence electrons. So only elements that come in with 1, 2, or 3 electrons have exceptions to the rule. So sulfur, is oxygen happy? The answer is yes. Is sulfur happy? The answer is yes. Everybody has 8 electrons here, and so everybody's happy. This is a completed diagram for this sulfate ion. All right, so this is ClO2 with a -1 charge. Okay, so first distribute your skeleton. Your loner is Cl, it goes in the center. Your oxygen goes on either side. You count your valence electrons. Chlorine has 7. Oxygen has 6 apiece, and there are 2 of them for 12. You've got a -1 charge on this ion, so that means add 1 more electron. So I've got 20 electrons to distribute. All right, so I've already used up 4 electrons just by putting the skeleton. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used up 16 electrons, 17, 18, 19, 20. Now I've used up all 20 electrons. All right, so because when I had extra electrons, they went on the central atom. So after I made oxygens happy, the extra electrons went on your central atom. So is oxygen happy here? Yeah, each of these oxygens has 8 electrons. Is chlorine happy? Yes. When I distributed the extra electrons to chlorine, 1, 2, 3, 4, 5, 6, 7, 8 electrons. So everybody's happy. This is a completed diagram for this ion. So SF4, count your valence electrons, 34 electrons. Your skeletal structure means you've used up 8 electrons. That's 8. That's what I'm going to start counting with, 8 electrons. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now I've made all of my elements happy on the outside, but I've only used up 32 electrons. Where do the other 2 electrons go? You have to distribute all 34 of your electrons. Remember, the rule said if you had extra electrons, distribute them on your central atom, and you could pick any of the 4 corners that are available on this molecule to distribute the extra electrons to. So I had said 32, so the extra electrons go on the central atom. 33, 34. So now I've used up all 34 electrons. So you place any open spot that are on the corners of your central atom. There's kind of an imaginary box around the central atom, and you put the electrons on any one of the 4 corners of this imaginary box. Now, it's a square here because I have 4 things sticking off of it. It would be on any of the open spots, if you had 5 things on any of the open spots around the pentagon that would be created around the S. So you find an open area. These electrons are going to change the shape of this molecule, and we'll learn more about the shapes that the molecules make based on their valence electrons in a PowerPoint called AXE. All right, so let's look at aluminum trichloride. So first I'm going to, oh, that's just aluminum chloride. That's not aluminum, it's a metal. So this is aluminum chloride. When you hybridize aluminum, how many bonds can aluminum hope to get at the most? The reason I'm pointing that out is aluminum is in column 3. Remember, elements in column 1, 2, or 3 do not get all 8 electrons. At most, he is hoping to get 6 electrons. He's hoping to double his electrons. And if he doubles his electrons, it means he will have 3 bonds. Remember, each stick is worth 2 electrons. So he's hoping to get 3 bonds. So when you make your skeletal structure for aluminum, it'll look like this. And the minute I made these 3 sticks to join these 3 chlorines, aluminum was happy. I'm still going to distribute my electrons. I have 24 electrons to distribute. So I started out with 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Be careful. We do not make a double bond for any of the exception to the rule elements. Aluminum is an exception to the octet rule, and it is columns 1, 2, or 3 elements that are those exceptions. So aluminum is in the column with 3 valence electrons and is happy with 6 electrons that it has. So this is a completed diagram for this structure. We do not borrow and make aluminum hold more electrons. So positive ions give away electrons. So when we count the valence electrons here, nitrogen has 5 electrons. That is not an exception to the rule element, so it's going to get all of its electrons. And hydrogen is 1 electron each. There are 4 of them. And remember, hydrogen's closest noble gas is helium, so each hydrogen is going to be happy with 2 electrons. Okay. And because I have a +1 charge, the reason I get a +1 is because I've given away an electron. So you have to take away an electron. So 5 and 4 was 9. And then minus an electron means I have 8 electrons to distribute. Draw your skeletal structure. Means nitrogen is your lone electron. He goes in the center. And then each of the hydrogens get bonded to the central atom. How many electrons have I used just with the sticks creating the skeleton? I've already used up 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Each stick is worth 2 electrons. So I've already used up the 8 electrons. Is everybody happy here? So yeah, hydrogen is happy with just 2 electrons because hydrogen's closest noble gas is helium. So that's an exception to the octet rule. Remember, we've always said, hey, remember, helium only has 2 valence electrons. And nitrogen is not in an exception column, but it has 8 electrons that it is sharing here with hydrogen. So this is a completed diagram this is ammonium. This is an ammonium ion. It's on your orange and blue chart in the noteworthy additions section. So this is nitric acid. We don't know our acid naming yet, so we would just call this hydrogen nitrate in the current naming system that we know. We will eventually learn how to acid name, but right now we're going to just call this hydrogen nitrate. So what's my first step? Draw the skeletal structure. I have 2 loner elements. 2 loner elements means I need to think if I have any rule that makes me know which element is in the center and which elements might be off to the outside. Now, I know that these oxygens are going to be on the outside, but I don't know at this moment whether to put nitrogen as my central atom or hydrogen as my central atom. So hopefully you wrote down your rules. Go back and see if there's a rule that helps you decide which element is the central atom. When you go back and look at the rules, you should see that there was an exception to the rule kind of thing that said, hint, hydrogen is terminal, which means it's on an end. So for this molecule, nitrogen is ending up being your central atom. So nitrogen is your central atom, and then you've got your 3 oxygens bonded to your central atom, and hydrogen is terminal, which means hydrogen is bonded to an end. You're going to count up your valence electrons. Nitrogen had 5, each oxygen had 6, and hydrogen brings 1 for a total of 24 electrons. I've already used up 1, 2, 3, 4, 5, 6, 7, 8 electrons just by making the skeletal structure. So I've used up 8 electrons. Create the rest of your octets. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Is everybody happy? I've used up all my electrons. Do I need to share with anybody? I've used up all 24 electrons. Are each of the oxygens happy? Yeah, that oxygen is happy. This oxygen is happy because it's got 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is happy. 1, 2, 3, 4, 5, 6, 7, 8. This hydrogen's happy with just 2. Remember, hydrogen only needs a stick. Never connect hydrogen with anything more than a stick because its closest noble gas is helium, which means it only needs 2 electrons. However, our nitrogen is not happy here. So we're going to need to erase 2 of the electrons. It didn't matter which 2 I picked. I happened to pick the 2 that were right here and create a double bond. Remember, hydrogen is a terminal element, which means it's not on the end. Which means it is on the end, and it's happy with just the stick of 2 electrons. So don't give it any more than 2 electrons. Don't borrow and have hydrogen have any more electrons than 2. Okay, go ahead and do some practice problems.